Alright, so as I said before, I'm going to talk about how to use this thing called Desmos. If you haven't used it already, it's desmos.com/calculator, and right here you can simply type any function. For example, we're working with trig functions, so say sine of x, and as you expect, you get these values. These are written in numbers, so this point here is 2 pi, right? But it's also just 6.28. Right? So this is what you would expect. So let's kind of look at some of the things that we claimed. For example, if it's 2 sine x, so you can see the time period doesn't change, but it just becomes bigger, right? Similarly, if I make it 4 sine x, it just becomes bigger, which is what we expect. However, let's say I change this to sine 2x, and you can see the blue sine graph is faster. It finishes at pi, so the time period is pi. If I make it 4x, it's even more squished. It's the green graph. Yeah, it finishes the cycle at pi over 2. But if I make it sine of 0.5x, then it becomes the purple one, which is ending at 4 pi. Yeah, so it's more spread out. So those kind of make sense. Now if you look at your notes, I asked there for you to see what happens if I add sine x and cosine x. Now this is interesting. I still get a graph that is periodic, right? It kind of looks like a trig graph. So adding these give me, let's say I plot them separately. Adding the red and the blue graph gives me the black graph. So that makes sense. Right here, this is going to be exactly double the length. It's going to be red plus blue added. And in some cases, the red is positive, the blue is negative, so they cancel out to get a 0. So you do get a periodic function. The second one that I asked you to try is sine 2x plus 2 cosine x. Now this is not like the graphs we've seen. It's not smooth, but it's still periodic in some sense. Right. So you can play around, change these and see. You can get a bunch of, in this case now it becomes a proper graph. In this case it's no longer proper. But there's still some sense of periodicity in all of them. Okay. Now the next thing on that sheet is plotting these three functions. Y equals x squared. Sorry, not 22 squared. Y equals negative x squared, and y equals x squared times cosine of 6 pi. So for pi you can just write pi and it converts into pi x. Okay, and you get this very interesting plot. I'm going to zoom in. Now what's happening here? You have this sine function, but it sort of has x squared and negative x squared as its boundary. So the question here is, what's happening? Why do these form a boundary? Think about it for a bit, and I'll talk about why in the next video. You can play around. What if you change this to x? And then you make that x. Again, the x forms a boundary for the sine function. What if I change this to x cubed I change this to x cubed, and I change this to x cubed. Once again, it forms a boundary. Oh, that's very interesting. Play around, put some functions, other functions that you know. For example, you've worked with exponential functions before. What if I add an exponential function here? And then just making sure I also change this to an exponential function. Wow, again, I still have this really nice boundary condition. Let's go a step further. What if I actually add a trig function here? Is that going to change stuff? Is it? Let's see what that makes that. Oh, that looks beautiful. So again, you have this trig function inside this other bigger trig function. Play around with this and see if you can come up with a viable hypothesis as to why is this happening? Is it always going to happen? And I'll talk about it in the next video.